Great. So we are happy to have Vini who will tell us about integrable systems and toric convex forms on top.
Thank you, Pazit. Thanks for the invitation to speak at the Zoominar again. Yeah, so today I want to tell you some things that about integrable systems and billiards that maybe some of you have already heard, and a few new ideas about how to extend these things to RP3 and even beyond some land spaces at the end. Okay, so I want to start by reminding you of what a toric domain is, since it's a very important object in this talk. So a toric domain is a set, for me in this talk, I'll just think of it as the pre-image of some set in the first orthant of Rn by the pre-image by the standard moment map. So it's the same thing as taking a subset in Cn that's invariant under the standard Hamiltonian toric action. But this way, we just kind of put the image of the moment map already in the set, sort of in the notation. So this is very well known and well studied. So like here are some examples. So the example on the left here is what we usually call the ellipsoid. So here's in 4 dimensions. So we'll call this EAB. Sometimes I'll put the 4 here to denote it's 4-dimensional. And then a particular case is a ball. So this is a B4. And on the right, we have a polydisk. And just to clarify, we put the pi. I put the pi here in the moment map because I want all the circles that generate the torus to have length 1 instead of 2 pi. So maybe like the real standard toric action, you would have 1/2 instead of pi. But I think people who talk about symplectic embeddings prefer that, because then that means the capacity of a ball with parameter C is C, the Gromov capacity. So that's just to make the capacity easier to read from the expression. Okay, so toric domains have studied a lot in the last at least 10 years, but more like 20 years in the context of symplectic geometry. And here are some special classes of them. So we have star-shaped ones, which are toric domains, they're star-shaped with respect to the origin. So that means the radial vector starting from the origin is transverse to the boundary of the domain. Oh, and just to clarify, I mean, a domain for me could be an open set or the closure of an open set, either one, depending on what we want to do specifically. But so I'll be a bit vague about whether domains are open or closed, but if you want to know for a specific case, something I'm talking about, if it's the open one, the interior, or the whole thing, you can ask me and I can clarify. So anyway, this is the star-shaped case. So on the boundary of the domain, this is transverse to the radial vector field, string from the origin. And this class of star shape is very interesting, because that's the ones where we definitely have a contact, where the Liouville form in Cn will give rise to a contact form on the boundary. And then we have monotone. So this is a class that Jean Gut, Michael Hutchins, and I defined a few years ago. And that basically is a class where the normal vector field to the boundary points or has positive coordinates everywhere. Like in dimension 2, it means, actually in every dimension, it means that it's the boundary of the domain is the graph of a function that's decreasing in every direction. And the significance of this class in higher dimensions, the thing that's nice is that for this particular class of toric domains, we know that all normalized capacities coincide. So that's one reason we care about monotone. And then there's 2 subclasses of monotone, which are concave and convex toric domains. So concave is, basically it's what the picture is showing you. You can talk about, so at every point, and you look at the tangent plane, and you want the surface or the hypersurface to be above it, and then the convex is the other way around. So those 2 cases are monotone. And then there is the weakly convex. And the weakly convex is something that the region is convex, but it doesn't have to be monotone. All right, so these are, these are, I guess I'm saying in dimension 4, but all of them, at least up to convex, maybe weakly convex, haven't thought about entire dimensions, but the other ones make sense in every dimension. But sort of the stronger theorems, most of them are only hold in dimension 4. So I guess the next question is, what's special about toric domain? So why do we care about toric specifically? So here's what I mentioned before, which is if you have a star-shaped toric domain, which is just star-shaped with smooth boundary, then we can look at the standard Liouville form. So it looks like this. So it's 1/2 of the sum of xi yi minus y dxi. So it has this nice shape. And we can actually write this in polar coordinates, kind of with some quotation marks. And so with these quotation marks, polar coordinates, this is just going to be like rho I d theta I. And these are polar coordinates in the sense that rho I is pi times zi squared, and theta I is the angle, or is the angle, the argument, sorry, is the argument of zi, but sort of in R mod z. So if we do this change of variables, then the contact form becomes very simple. And then it's easy to see that as long as the domain is star-shaped with respect to 0, to the origin, then this lambda 0 restricted to the boundary is a contact form. And then this is like a very classical calculation. I mean, this was done, I don't know, for the first time maybe 20 years ago, or maybe even more, I don't know. But it's still maybe interesting to remark that when you have the situation, then the rate vector field is parallel to something that has this expression. So you look at the normal vector field at the point at the vector ρ1 through ρn, as I drew here in the picture on the right. And then you basically, each coordinate of the normal vector field, you multiply by del theta I. And that's going to give you the direction of the rate vector field. So, I mean, that's what that's saying is like basically, first of all, like the rate vector field is, the rate flow preserves these tori. So above every point here on this curve, we have a torus, except that when you reach the axes or the coordinate planes, then you have a smaller torus, a torus of smaller dimension. In this case, in the 4-dimensional case, you just have a circle. And the rate flow preserves this. So it's a very, very special kind of rate flow. So we can understand a lot of it. So that's one of the reasons we like toric domains. So we can really understand the contact flow, the rate flow very well, and we get all sorts of nice consequences from it. So let me explain a little more. So for example, so if we fix a point on the boundary of omega, and we let ρ1 through ρn denote this outer normal vector. So then we have two possible situations. So either this normal vector field, this normal vector is an integral vector. So it's parallel to something in Zn. So that means that, you know, the quotient of all the different variables, that's always rational. So in that case, what that means is, you know, that all the Rabe orbits will eventually close. So we get a torus of closed Rabe orbits, and it's not hard to see that they all have the same period. So, you know, and they're just they're not dense. So, but otherwise, if basically if there exists two coordinates of the outer normal vector whose quotient is irrational, then the Rabe flow can't close up. So then we're going to have this torus foliated by dense Rabe orbits. Okay. Yeah, so in the case when this, in the first case, so when we have a torus of closed Rabe orbits, we take, for example, a vector, a normal vector that's primitive. That means, you know, the GCD of at least two coordinates, of all the coordinates is 1. So that means you can't find, you can't write it as an integral multiple of a vector in z to the n. And if you take a simple closed orbit, then we also have a formula for the action, which is the period. So it can be expressed in this pretty easy way. Like it's just the dot product between the point and, so if this is your domain, then you look at this is row and this is nu, and you just look at the dot product between row and nu. So it's very easy to compute. I guess the conclusion is just very easy to compute. So we can, for example, we can understand the spectrum very well. We can compute capacities. I mean, it's not, these things are not so easy. You need a lot more background after this, but to compute capacities, for example, capacities are usually complicated to compute. But anyway, you can do all of that. This is just the starting point. And then we have some very strong theorems about symplectic embeddings of these domains. So for example, McDuff proved in 2009 that basically using the ECH spectrum that comes from these toric domains, for the simplest kind of toric domain, which is the ellipsoid, an ellipsoid embeds into another if and only if the ECH capacities don't obstruct that embedding. So that was a very interesting result that built on the work of many other people. And basically she did this by creating a ball packing, by basically saying that this symplectic embedding of an ellipsoid into another one is equivalent to a certain ball packing of a certain ball. And then she looked at the spectrum. I mean, she didn't exactly use ECH on her paper, but in some more way, she was using, I mean, she was looking at the spectrum, which is not, we don't really need ECH to compute the spectrum of the ellipsoid. So anyway, and she got the numerics that the ECH capacity gives you as well. And then a few years later, Dan Christopher Gardner generalized this result to a, yeah, so this is only in dimension 4. I should clarify that if you take two toric domains, one of which is concave and the other is convex, then the concave one embeds into the convex one if and only if ECH capacities don't give you an obstruction to this embedding. So in other words, ECH capacities are sharp for the embedding of a concave toric domain into a convex toric domain. And he also did this using a certain ball packing. So he proves that this symplectic embedding exists if and only if a certain ball packing exists. And then he proves that the ball packing exists if and only if there's an inequality of ECH capacities. Okay, so before I continue, are there any questions or comments? Okay. So so far, you know, you've seen how toric domains are quite nice. There's a lot that's known about them. And what I want to tell you is I've been for the last several years, I've been hunting for toric domains. And of course, you can always draw something and look at the pre-image, but it's more fun if you go in the jungle and you start looking for them when they're not, you know, right there in front of you. So I call this toric domains in disguise. So toric domains that are hiding. So the first one that I found was D star of D2. So if you look at your disk in R2 with the flat metric, and you look at the disk bundle, so that means, you know, in the unit in the cotangent bundle, you look at the unit disk on each fiber. So this disk bundle of D2, which you can also think of as the Lagrangian product of two disks, because the metric is flat. This is symplectomorphic to a concave toric domain. So that's a result where I introduced the study of the use of integral systems to basically find toric domains so that we can study symplectic embeddings of them. And the idea, which I'll talk a little bit about later, is that the Hamiltonian dynamics on the boundary of this domain, which have a lot to do with the domain itself, as probably most of you know, are basically the billiards, are basically billiard dynamics in the disk. And then you can use the Arnaud-Liouville theorem to get that. And one other thing that we can get is if we draw the toric domain that we obtain. So let me do a quick drawing. So I mean, this is I'm gonna do an approximate drawing, but this has an expression for it. And the thing that's cool here is that you can actually see, so the rate flow, I explained how you can see in the toric way on a toric picture, but this corresponds exactly to the billiard flow in D2. So this is a little bit stronger than what I have in the paper, because in the paper I showed like the interior of some domain is symplectomorphic to the interior of a toric domain, but actually even on the boundary, it's something singular is happening. And I haven't written this down completely, but you can definitely see a correspondence between the dynamics on the boundary, which is this billiard dynamics, and the toric, the dynamics of the rate flow on the boundary of this toric domain. So this is kind of the bonus part of the result. Which, I mean, it's not that useful because we already understand billiards on the disk, that they're pretty simple, but it's still kind of cool to see them. It's even easier when we have the toric domain. Okay, so the next example that I want to tell you is now it's a Lagrangian product of the hypercube, so I to the n, interval to the n, and the dual body of the hypercube, which is called the cross polytope. So I drew a three-dimensional picture here. So that's basically the L infinity, the unit ball in the L infinity norm and the unit ball in the L1 norm. And the result is that that's symplectomorphic to a ball in dimension 2n. And I didn't put a number here, but this is like the Euclidean ball. So if you take the product of the hypercube and this cross polytope, we get something, we basically get a ball. And I think that's actually kind of surprising. And at the same time, maybe not extremely surprising if you're used to playing these funny billiard dynamics. You see that you basically have a Zoll situation. So that's kind of what you would expect. And we have equality in Viterbo's conjecture, which of course now we know that it doesn't mean that much, but apart from just one example, we still think that all the other examples that we know, we still get some intuition. And I attributed this to Trainer because she kind of had the idea of removing the ball from the axis, and I guess it follows from her work basically that we have a symplectic equivalence. But to get the symplectomorphism completely in all dimensions, I think that I can only do with integrable systems, my work with Sepe in 2019. Okay, any questions? Okay, so a more interesting example, a more surprising one, is what happens when you take the Lagrangian product between, say, a triangle and a hexagon. This is another case that's been known by the Minkowski billiard experts for several years, that you get a Zoll billiard flow, and you get systolic ratio 1, so it kind of should look like it should be a ball, and indeed it is a ball. So we proved that with Johan Ostrover and Daniele Sepe and in 2023. And actually, we can generalize this to higher dimensions. So given a simplex, we can find a polytope, which is basically generalization of what the so-called rhombic dodecahedron, and so that the product is symplectomorphic to a 2n-dimensional ball. So I'm not going to draw the rhombic dodecahedron, but it's a well-known polyhedron in dimension 3, and then we can generalize this to higher dimensions. So I think this is kind of very interesting because it involves these other polytopes, and this has to do with the proof has to do with total lattice. It's quite intricate. Okay, but now I want to talk about a different family of examples, which are not Lagrangian products, but are disk bundles. So now, if you start looking at disk cotangent bundles of non-flat metrics, then interesting things start to happen. So the first example, this is actually one of my favorite examples of these toric domains in disguise, is what happens if you look at a hemisphere. So this is a half of a flat sphere, and you look at the disk bundle of this hemisphere. And we can prove that this is symplectomorphic to a ball, a 4-dimensional ball. And again, if you look at the rate flow here, it's not too surprising in some way, because what's the rate flow here? So, the rate flow is the geodesic flow, but because you have a boundary, and you have the disk, that really what you're supposed to think that it's a geodesic flow with a billiard reflection on the equator. So this basically looks Zoll and smells Zoll, and I guess it is Zoll. I don't know if we have quite a definition for Zoll that encompasses this, but this should definitely fulfill all of the possible definitions. Anyway, we can prove that the interior, the open manifolds here are symplectomorphic. And we can actually go a little further. So if we try to extend this to the whole sphere, we have a problem with topology that it basically, the disk bundle of the whole sphere can't be a toric domain because it has the wrong topology. I mean, the boundary is not an S3. But if we remove a fiber, then basically now we don't have, we remove the topological problem, and we can prove that the disk bundle is symplectomorphic to a toric domain. In this case, it's actually a polydisk. So it's P 2 pi 2 pi. Okay, and this is joint work with former student Brian Ferreira in 2022. Okay. And here, I mean, I'll come back to this idea later in the talk, but what you should think about here, like what is the Hamiltonian system in something like this? I mean, basically we have the geodesic flow, but we're removing a fiber. So what this means is like, this is the geodesic flow everywhere, but then when you have the orbits that are going to hit the South Pole, what happens is you have a billiard reflection there. So that's kind of removing this fiber means that in some ways you put a needle here, and it's a needle that doesn't have any thickness. So if you hit the needle, then you bounce back. But if you don't hit the needle, then you just keep going with your geodesic. So that's the Hamiltonian flow that's represented here. And this kind of lack of continuity of this flow is represented basically by the fact that the polydisk has a corner. It's not, the boundary is not smooth. Okay? Any questions about that? Yeah, so I guess the idea here is that, by removing a fiber, we kind of are introducing a billiard reflection at a point. And then we still get a toric domain. Okay, so now I want to talk about another class of metrics on the sphere. So for example, if we look at, so this is a EABC is going to be an ellipsoid in dimension 3. So this is not the ellipsoids that I mentioned before. This is just the shell of a three-dimensional ellipsoid with parameters ABC, just like in an analytic geometry notation. Okay, and I'm using this curly E to differentiate. So if we look at the ellipsoids of revolution, so the ones that are invariant under an S1 action, on say the X1 action that rotates the X1, X2 plane, then we basically take the first two parameters to be the same, and we can normalize them to be 1. So what we can do is we can look at E11C for some C. And we can do the same thing that we did for the for the standard sphere, for the round sphere, for this guy. So this is basically just changing the metric on the sphere to a metric that's S1 invariant. And it's ellipsoidal. I mean, it's not any, it's an ellipsoidal metric that's S1 invariant. And then if we remove the South Pole again, and we look at the disk bundle, we also get, this is also symplectomorphic to a toric domain. So this is a result that I proved with Brian and then another former student, ℝℙ3 Vicente, in 2023. And it's kind of interesting because the behavior of this toric domain is changing with C. And basically there's a dichotomy or trichotomy, I guess. If C equals 1, we have the polydisk, which we proved before. If C is less than 1, we have this funny domain, which kind of looks like a concave toric domain, but it's not exactly a concave toric domain. It looks like two pieces of a concave toric domain. And if C is greater than 1, this is also kind of a funny domain. This is a weakly, what I call the weakly convex toric domain. But all of them have these sharp, the sharp corners. And these are always have 90 degrees. So this kind of if for all C that these corners are a 90-degree corner. And I guess we should see this as like this corner is a consequence of the fact that we're putting a needle, we're removing a fiber. So that's the same thing as putting a needle there and having billiards there. And that creates a discontinuity in the flow. So that's kind of why this thing that like the geodesic flow and ellipsoid of revolution, which is a perfectly smooth object, gives rise to these really funny toric domains. Okay, but anyway, we can prove these symplectomorphisms exist. And then it's cool because we can use this to compute the Gromov width of the ellipsoids of revolution. So and the other thing that's nice is we can visualize the geodesic flow, just like I told you for the billiards on the disk and all these situations. We can visualize the geodesic flow on the boundary of the ellipsoid, and that's not so easy. I mean, there are papers about it. It's understood, but it's not very easy to put your hands on it. But once we transform the ellipsoid of revolution into a toric domain, then we can basically see all these amazing properties of the geodesic flow of the ellipsoid. So, for example, there is this nice property which maybe some of you who have looked at the geodesic flow of ellipsoids are familiar with, which is that if this parameter C is less than 1/2, so so that's called it's very oblate. So if the ellipsoid is very oblate, then there is a new family of simple geodesics that goes up and down twice, which I drew here, and it's an S1 family. Of course, everything has an S1 symmetry. And in fact, as C gets smaller and smaller, we're going to have more and more of these geodesics that kind of go up and down many times. And that has to do with the fact that, let me go back to this picture. So when you look at the angle that this thing hits, this angle, it gets closer and closer to vertical as C gets closer and closer to 0. So the first moment where this slope -1 appears is exactly, the slope -1 exactly corresponds to this trajectory here. And then when you get slope -1/2, -1/3, and so on, you're going to have these other geodesics that, let's see if I can draw, that are going like this. So they only exist, these simple geodesics that oscillate like that around the equator, they only exist for C small enough. And I mean, the calculation that is in the previous papers, it's pretty hard to remember, to understand. So I find it very satisfactory to be able to transfer all the calculation basically to the moment map. And in the moment map, we have basically all the elliptic integrals. And then once you have the moment map, you can see everything in the toric domain. So that's one thing, one consequence of this theorem. And the other one is we can compute the Gromov width. So the Gromov width, so before I tell you what the Gromov width is, let me just define these two numbers. So for C less than 1/2, we have this special orbit that oscillates, goes up and down, up and down. And I'm going to call that length alpha of C. So this alpha is only defined for C less than 1/2. And I'm going to call beta of C the length of the meridian, of any meridian. There's an S1 family of meridians. They all have the same length. And if C is less than 1, then these meridians are less than 2 pi. And if C is greater than 1, then the meridians are greater than 2 pi. And of course, as C grows, beta grows. So beta is an increasing function in C, and it goes to infinity as C goes to infinity. Okay, so here's the formula. So the formula is the following. So between 0 and 1/2, the Gromov width is given exactly by that alpha of C. So that the length of that funny new simple geodesic that appears around the equator. From C between 1/2 and 1, it stabilizes at 2 pi. So I guess I didn't say that as C goes to 1/2, that orbit that oscillates around the equator, it converges to the equator. So it disappears on the equator, basically. And again, you can visualize that in the toric domain. So, converges to 2 pi, and then it's equal to 2 pi between 1/2 and 1. And then it starts being equal to the meridian. So it's equal to the length of the meridian, what I'm calling beta of C, until this length is equal to 4 pi. And then 4 pi, it stabilizes, and it's 4 pi forever. So this is, again, appeared in the paper that I wrote with the same paper. So with Brian Ferreira, myself, and ℝℙ3 Vicente. Okay, so that's the formula for the Gromov width. Any questions?
What about other capacities?
Other capacities. Yeah, so we haven't computed many other capacities, or I think we haven't computed any other capacities. So I'll tell you at the very end of the talk a strategy for computing ECH capacities. So we actually didn't compute ECH capacities for this. With Brian Ferreira, we computed ECH capacities for the disk bundle of S2. And it was kind of hard. So we didn't try to, we just computed a couple of ECH capacities, enough to give us the obstructions that we needed to compute the Gromov width. Computing all of them in principle, like by hand, just using the geodesic flow or the rate flow would be, I think, pretty hard. But I'll tell you at the end, the light at the end of the tunnel for computing at least ECH capacities. I'm not sure about, other capacities. Yeah, maybe Johanna Bimmerman knows how to compute Hofer-Zehnder capacities. I think she might know. But yeah, as far as good Hutchings capacities, for example, I don't know. Oh, one thing to notice is like the historic domains are they are embedded into the disk bundle of E11C. So computing the capacities for the toric domain is not the same as computing the capacities for the disk bundle. They don't coincide in general. Like, sometimes some of them might coincide. They have the same volume. It's a volume filling embedding of a toric domain into this disk bundle, but the capacities don't coincide in general. Like, for example, C1 usually doesn't coincide, the first ECH capacity. So, and the Gromov width is sometimes C1, but it's usually not C1. So that's another thing to keep in mind, that the toric domain is good to give us the Gromov width in this case, but it's not good enough to give us all of the capacities. Yeah. So I'm going to talk more about part of the point of the talk is to go beyond this example, or beyond the removing a fiber. So the question is like, okay, we removed the fiber, we got a lot of things, but what if we try not to remove the fiber? Because if you think about the geodesic flow on the sphere, on the ellipsoid of revolution, there is no singularity. I mean, it doesn't really see the poles, the North Pole, the South Pole. So like, let's try to not remove the fiber. And the problem, the only reason we remove the fiber is that when you look at the boundary of the disk bundle of the sphere, that's an RP3 and not an S3. So like, it doesn't have the topology of a toric domain. And that was kind of the only problem at first. So now what we can do is we can try to talk about more general toric domains so that we would fit this case. So that's what I'm going to do right now. So let's talk about toric contact forms on RP3. So as I just mentioned, the unit cotangent bundle of S2, I think it's well known that it's diffeomorphic to RP3. And basically, we kind of know that T start of S2 is already toric in kind of its own way. Like, it's not a toric domain, like a subset of CN. But it admits a simple Hamiltonian toric action with momentum map given by this, like basically the norm of P, and then you look at the angular momentum, the third coordinate of the angular momentum, so Q vector product with P, and you look at the third coordinate, and basically it's well known, it's easy to check that those two Hamiltonians commute with each other, and both of them have all the orbits have length 1 or 2 pi, depending on your trivialization, on the size of your torus, of your circles. So basically this gives us a momentum map, and then the image of this is a cone like this. So it's the cone that lies in between the x equals y and x equals minus 1. Okay, and then I put like minus, you remove the zero fiber if you want to get smoothness. But I guess it's smooth if you don't remove the zero fiber, you still have a map. And all that you have to see is like, at the origin here, we have this zero fiber. Okay. Any questions? So here's an example. So for example, we can look at the disk bundle of S2. This is just the subset of the cotangent bundle of S2, such that norm of P is less than 1. I think actually I inverted the coordinates here. So let me fix this. I think I want to first take the momentum and then take, yeah, my picture is like this. So if I look at the set, this is just the set of points QP, where P is less than 1. So the picture is exactly this. And now we have this picture, we can try to basically play the same game of the definition that we did with the definition of a toric domain with this picture. So we can define RP3 toric domains. So that's what I'm calling an RP3 toric domain. I don't know if there's a better name for it, but for now I'm going to call it an RP3 toric domain. Is basically the pre-image of a region in this cone V by this moment map mu bar. And as far as I know, the first person to write this down is my former student, Jonathan Trellis, in his thesis. And we can basically call something like this on the left a concave RP3 toric domain, and something like this on the right a convex RP3 toric domain. And what's the definition of concave and convex? I guess basically the same thing. Like you take a point. If it's smooth, you take a point and you take a tangent plane, a tangent hyperplane, and you want the boundary to be either completely above or completely below, whether it's concave or convex. And I'm not going to talk about the idea of extending weakly convex. I think it's possible, or monotone, but let's just keep it concave and convex in this sense. I think this convexity here is the more general type, like what I call the weakly convex in the other case. But anyway, it's not going to be, this distinction is not going to be very important for this talk. Okay, so we can talk about concave and convex RP3 toric domains. And what we can prove in an upcoming paper with Brian Ferreira and Urs Farnfelder is that the disk bundle of the ellipsoid of revolution, the entire thing, is actually symplectomorphic to one of these, domains. And now the picture becomes a lot prettier, because in the case C equals 1, we get the flat thing, which is basically just the disk bundle of the sphere. And then if C is less than 1, we get a concave RP3 toric domain. And if C is bigger than 1, we get a convex RP3 toric domain. Okay, and I mean the formulas. I'm gonna explain how the formula comes. I didn't put any formulas in this talk because I think the formulas aren't too helpful. But just to tell you, we have explicit formulas that involve elliptic integrals for all these things. And that's how we get, for example, the gram of widths. And then when we have this idea, we can try to generalize this. And we can say, well, now if I take a region, say a star-shaped region in this cone, and I see it as an RP3 toric domain, can I try to do a procedure to get like a genuine toric domain that's embedded in there, basically by removing just the fiber? And the answer is yes. So basically, there is a way of taking one of these RP3 toric domains, and then you remove the fiber over the south pole, say, it could be the north pole, and that's symplectomorphic to a toric domain where the domain is just built from this original omega C. And the formula to go from one to the other is pretty simple. It's just something it's written here. So it's basically a linear thing multiplied, a very simple linear map multiplied by 2 pi, or a linear map by parts. And the by parts really is kind of it will take the two sides of omega c and it'll make two linear things, two linear transformations, and then it'll create this corner that we were seeing in the other result. Okay, so there will be a corner here. If this is smooth here on the left, there will be a corner on the right. But still, like sometimes there might be things that are easier to see directly in the toric domain. The other thing I should say is like there's also a strict contactomorphism from this boundary to the boundary from the boundary on the left to the boundary on the right, except for the point where you don't have smoothness. So we can see the toric flow, rate flow in either situation. And in fact, in the calculations at the very beginning, when I talked about the rate flow, we didn't really need to be like in a regular toric domain. Like this RP3 toric domain basically would have the same calculation for the rate flow. So if we just change our muscles a little bit, we can start doing things directly with the RP3 toric domain and get probably most of the results that we want without having to go to the usual toric domains, which, for example, won't compute all of the capacities. Okay, any questions? So here's some more general examples. So a Finsler metric, I think everybody knows this, but just to be everybody to be on the same page, a Finsler metric on S2 is, it's a map from the tangent bundle to the set of non-negative numbers, such that at every point on the base, we have a Minkowski norm on the tangent space. So it's basically a norm on every tangent space. That's not necessarily symmetric. So it's just positive homogeneous, and it satisfies the triangular inequality. And so it's more general than a metric. So this we have geodesics, but the geodesics are not reversible. And so we can. It's not. I guess. So another thing we can prove is that if you have an S1 invariant Finsler metric on S2, then when you look at the disk bundle of S2 with respect to this Finsler metric, so at every point you look at the ball of radius 1 with respect to this Finsler metric, that is symplectomorphic to one of these domains. So that's a generalization of the result for the ellipsoids of revolution. So there exists some omega like that. Okay, so any questions so far before I go on to the proofs? Okay, so let me go to the proofs. So the main idea of the proof is to use the Arnaud-Liouville theorem. So the Arnaud-Liouville theorem is a very classical theorem, appears in Arnaud's famous book. Somehow it's not used that much by symplectic topologists, but I use it a lot. I like it a lot, and it's been very useful to find these toric domains in disguise. So this is what it says. So if you have an integrable system, so if you have basically n Hamiltonians, which Poisson commute, I forgot to write. So the Poisson bracket is 0. And we pick a regular value of the total map when you put all the Hamiltonians together. And it has one important property, which is that the pre-image is compact and connected. Then the pre-image is diffeomorphic to a torus. So this is the first part. So the fact that you have these n commuting Hamiltonians, it means that basically the flows don't interact with each other. And then the fact that it's compact and connected means that basically you can show that it closes up and it has to be a torus. Okay, this is not too hard to prove that. But then the even nicer thing is that we can find action angle coordinates locally. So that means that it's locally we have a trivial Lagrangian fibration. So that means the following. It means that there exists an open set and a diffeomorphism between this open set and another open set, and there's a symplectomorphism between the pre-image of this open set up in the symplectic manifold and the trivial product of V and Tn. So this is the Lagrangian product, such that this diagram commutes. So this map psi is a symplectomorphism, and this map phi here, sorry, this is a capital phi, and this is a lowercase phi, is a diffeomorphism. Okay, so this is basically saying that this map F, so the integrable system altogether, it's locally a trivial Lagrangian fibration. That's what it says, that these action angle coordinates are basically this. And we can actually compute this a candidate for phi explicitly. And in the following way. So we choose a primitive for omega in the pre-image of U by F. And then for each point on the base, we know we have a torus upstairs. So we can choose a collection of simple curves in the torus that generate the first homology of the torus. And we choose a collection of such curves, of course, varying on the point on the base X. We want these simple curves to vary smoothly on X. So we can always do that. And then what we do is we integrate the primitive along all of these gamma I x's. And the theorem is that basically there's a lift of this phi to a symplectomorphism, capital Phi, such that this diagram on the top commutes. Is that clear? So that's the recipe to compute sort of like all of these things. So in this case, let's see how we prove this particular case. So let's say we have the disk bundle of a Finsler metric on S2. So how do we get this Y sigma? So what we do is we take the two Hamiltonians. So the first one, this is a 4-dimensional case, so we only need two Hamiltonians. So we look at the norm, the Finsler norm of P squared. And then we look at the angular momentum, the third coordinate of the angular momentum. And I'm not going to, of course, the expression for the Finsler norm is, depends on the Finsler norm, of course. But we know that we suppose that it's an S1 invariant Finsler norm. And that's all we need to see that these two Hamiltonians commute. Because the Hamiltonian vector field of the angular momentum, the third coordinate of the angular momentum, is this del del theta. So that just kind of rotates. The del del theta is the theta is the coordinate, is the for me here in this proof is the angle, is the argument in the x1 x2 plane. If we think about for example, if you think about cylindrical coordinates, for example, on the sphere. And of course, the H is going to be very, very complicated if you want to write this down in cylindrical coordinates, for example, if the Finsler metric is very complicated. But it doesn't really matter because at least to prove the existence of a domain, so we get that the Poisson bracket is 0, and the pre-image has to be compact. Basically because the manifold that you start with is compact. So the compactness is easy. Connectedness is you have to think a little bit. But anyway, we can apply the Arnold loop here. And then we have to find the loops. And I mean, I'm not going to tell you how to do all of that, but you can do. The thing to notice is that we only get singularity. So like a place where you don't have a regular value exactly at the equator. So you get the equator twice. So you get the equator once, and you get the equator going back. Yeah. So anyway, this is and those will correspond to the kind of the points where we have to be on the boundary of that cone. Okay, so that's the first part of the proof. And then the second part is, and sorry, I think for this part, this is actually in progress, so this is kind of a disclaimer, and I'm explaining the proof to you as we're realizing it. I mean, this proof definitely works in the case where the Finsler metric it comes from the ellipsoid of revolution. For more general Finsler metrics, I think that this is a little bit subtle. So maybe let me just say, I'm not doing this for Finsler metric in general. I'm just doing this for, I'm just proving this when the Finsler metric is induced from when you look at the diffeomorphism that takes E11C to S2. So you can take the round the Euclidean metric on the ellipsoid of revolution, and that will give you a Finsler metric on S2. And then for that thing, this works. So that part of the claim I'm not 100% sure is correct. Generalizing this to Finsler metric maybe is the really in progress part. So maybe I shouldn't claim that very much. Anyway, proving this for the ellipsoid of revolution. Okay, so we get this domain y omega. And then the second part of the proof, and this is the part that now I can forget what my original domain is. I just take some RP3 toric domain. So whatever RP3 toric domain I have, so it's a region in that cone, and I remove the fiber at the South Pole or the North Pole, and I claim that that's symplectomorphic to a toric domain. So this goes back to the idea that we had in the paper with Brian and Alejandro. But now, because we already have in RP3 toric domain, we kind of were almost there. So we basically already have this this J and the H. So this is this Y omega is already RP3 toric. So all we have to do is have to remove that fiber. So removing that fiber, in terms of integrable systems, what that means is we change the Hamiltonians, and now we have to basically put a potential that's exploding as we get close to the pole. So I put a Hamiltonian here, like 1 over Q3 plus 1. And this is going to plus infinity when the coordinate Q3 is going to a minus 1. And then I put an epsilon here. So this is the kind of the strategy of proof. So what this Hamiltonian is doing is approximating billiards reflected on this point. And now if you put these two Hamiltonians through the Arnaud-Liouville machine, then what happens is you're going to get another domain, and this domain is this omega tilde. And then basically at the end, as epsilon goes to 0, as epsilon goes to 0, you get the domain omega tilde. And then maybe it looks like you would get the same domain, because like the epsilon's going to 0, you get the same thing. But the subtlety here is like when you look at the loops that you need to apply the Arnaud-Liouville theorem, what happens is the loops can't go to the South Pole. So you have to find a way to get a smooth collection of loops that includes these loops here, that includes the loop that kind of go in the direction of the South Pole and come back. That's continuous, that's smooth. And then you need an extra trick that actually you used before. And then this extra trick, it basically will mean that the image of the moment map that you obtain is going to have this corner. And then the map is exactly the map that I had written earlier, which is here. So this is the map that we get after we apply the action angle coordinates. And then to finish up, I should say that there is a more general setting, which there's a lot of interesting things going on. And this was introduced by Jonathan Trejos in his thesis, so this case of the RP3 toric domains, RP3 is L21. So we can now think about toric domains in the LP1 or even LPQ toric domains, I guess. So that is basically the following thing. You take a cone in R2, and here I'm just looking at the LP1 because we hope a little more for LP1, but I guess you can even think about LPQ. So you just have to basically take the normal to be PQ or QP or something with minus and pluses. Or maybe, yeah, I think like PQ in this direction, something like that. And then you can basically just take this cone multiplied by T2, and then you quotient along the two lines by the normal vector, by the direction of the normal vector. And then this is kind of a well-known thing that the manifold that you obtain when you connect this line to the other line that is an LPQ. So you can do the same thing, and then you can talk about toric domains in this setting. And you can talk about, you can define concave and convex ones. And I think there are a lot of interesting questions about this. So, for example, I mean, Jonathan proved in his thesis that if you take a concave one, then we can come up with a ball packing, basically like this. The first one, you take the horizontal line until it hits the boundary. And that's not a ball, but that's basically, I mean, in the case of RP3, that will be like a disk bundle of S2. But this is like a very specific thing that's kind of like plays the role of a ball. And then the rest, we can fill the rest by genuine balls. And he proved in his thesis that this ball packing computes the ECH capacities of this domain. So, for example, if now we go back to the ellipsoid 1,1C for C less than 1, then we can actually compute ECH capacities for D star of V11C, because this is the case of P equals 1, P equals 2. So, I mean, I like to draw this case like this, but we could also draw like a line like this by an affine equivalence. And then we can use ECH capacities to compute these. We can use the ball packing that Jonathan defined to compute the ECH capacities for this guy. So that's an answer to a question from before. And then there are some. So this is what he did in his thesis. But then there are some follow-up questions that I think are very interesting. So first of all, what about the concave guy? So people who know about ECH capacity and toric domains probably know that we have this kind of old way now to compute the capacities of concave toric domain with the ball packing. But then there's also a way to compute ECH capacities of a convex toric domain by some kind of a ball co-packing. So you pack with balls from the outside. So I guess it's still not known if you can do the same thing for this length space version of the toric domains for a convex. So this would be what we would need to compute the ECH capacities of this bundle of the ellipsoid of revolution when C is greater than 1. Because for that case, we have a convex domain. This is for C greater than 1. So I think that's probably true, but I'm not sure. And then I guess the last question is, are ECH capacities sharp for embedding these lenticular concave toric domains into the lenticular convex toric domains? So that's what I have for today. Thank you.
Thank you. Are there any questions? Oh, I see there's some question in the chat.
Well, maybe I have a question. So, do you think it's feasible to prove a kind of abstract result which says that integrable system with this and that properties is a toric domain, or RP3 toric domain? So, in the spirit of Fomenko's work, for instance, yeah. So he had a lot of work trying to classify energy levels.
Yes.
Exactly. Yeah, three-dimensional energy levels.
Yes.
So what you can say about this?
I mean, I'm not sure I understand the question exactly.
So
But I
the
mean,
question is the following: assume that I have integrable system with
yes,
certain restrictions on singularities,
yes,
right? So I have foliation by invariant tori with,
yes,
with some restrictions on singularities. So
yes.
then, if these restrictions hold, so then the kind of, let's say, the energy level is the boundary of a toric domain, or P3 toric domain,
Yeah.
depending on singularity.
I mean, I think that the philosophy here is that, to get an actual toric domain, the restriction on the singularities is very, very strong. Like, because the singularities have to be this like Hopf-Link or something very, very strict in higher dimensions. But if you have an integrable system, it might have singularities that are not like that. For example, like, the disk bundle of an ellipsoid of revolution. And in that case, like, I think part of this definition is to make the definition of a toric domain more flexible. I don't know if that's what you're saying. If you have this hypersurface that, I mean, if it has the right topology, if, like, the hypersurface is in C2, so the hypersurface, it's something that is an actual 3-sphere, then this generalization doesn't work. But there are other generalizations that I didn't talk about in this talk of things that are kind of almost toric in some sense, like it's toric almost everywhere except for these singularities, and we just have to understand how the singularities are interacting with the rest. But to be a toric domain, it has very strict. I mean, it's very restrictive on the singularities. So that's why I'm trying to go beyond toric domain. Does that answer the question? Or?
I would say meant the following, that you passed through a number of examples and
Yes.
showed that these are either toric domains, so these are P3 toric domains or length space toric domains. But
Yeah.
the question is whether there exists a master result, which says that if something holds, so then it is a toric domain of this class. And so then you just substitute your example. Yeah, you have really a lot of various examples into this master result and kind of get.
I think, like, all these, like, the different definitions, like, the usual toric domains, the RP3, the length space toric domains, they have different topologies too. So, like, kind of, if something that we already know that we're trying to prove, yeah, I mean, how can I answer your question? I think that the answer is, hopefully one can get to a general result that says if the singularities are like this and the topology is like this, then this is the toric domain of the right topology. I think that's the desired result. So yeah, I think it's possible if we, and this is maybe like an integrable systems question, like, if we can describe the singularities and the singularities are prescribed, it's like elliptic singularity or something, then we probably can say something. But even with S3, like, we already have examples that are kind of complicated. Like, for example, if you look at the ellipse times the disk. So, that is the Hamiltonian flow there is billiards in the ellipse. So it's very known forever that these are integrable. This is an integrable system, but this is not a toric domain in the classical sense. So we're still kind of working on figuring out what kind of domain this is. So, it's because the singularities are funny, like you have this hyperbolic orbit in the middle. So we have to expand. I mean, the next kind of one possible other extension in a different direction that's not in the topology, but it's kind of in the dynamics, is by considering like S1 invariant contact forms, which are toric almost everywhere. And then, they have to do with looking at like these pre-quantization bundles, and basically looking at Morse functions on S2 that are kind of complicated. So that's one possible extension. Like you take a Morse function on S2, and then you pull it up to S3 by the Hopf map, and you look at the fillings of that. So that's one possible extension. And I think one might be able to show most integrable systems will give rise to a toric domain of that sort. But I don't know, because I thought the ellipse times the disk was one of them, and one of my students told me a couple of weeks ago that he doesn't think so. So yeah, I think it's very much an active question for me.
Thank you.
Thank you for the question.
Can you say something when the ellipsoid is not an ellipse convolution, like one in
Yes.
T?
Yeah, so that's related to this question of the ellipse. So if you take an ellipsoid that's not a revolution, this bundle, of course, it's a geodesics on the ellipsoid, which we also know it's integrable. But it's similar to the kind of the billiards on the ellipse. It's integrable, but the singularities are much more complicated. So we have these like umbilical points. I don't know if for people who know geodesics and ellipsoids, have these umbilical points, and you have like hyperbolic orbits and elliptic orbits, and it gets a lot more complicated. So what I was hoping is that it would be an RP3 version of this this thing I just described, which is you take a Morse function on S2, and which is not a perfect Morse function, and then you lift it up to S3 and you fill it. So if you did something like that for RP3, but I don't know, I have to think more about that case. But it's one of those cases that Leonid was saying, like it's integrable, so we would like to say something about being the toric domain, but we need to figure out what we mean by a toric domain. What is the right definition that's going to fit all these things? So I think there should be something for the ellipsoid, the triangle with different parameters, but I don't know exactly what it is yet.
Do you have something similar to the condition of being monotone, so that all capacities coincide in this case, or something?
That's a very good question. I don't know. Yeah. Yeah, I thought about it yesterday, actually, when I was preparing the talk. I mean, I think it's not so, yeah. No, I guess the answer is no. I can have some guesses, but I don't think I can see any, because even like thinking about what the cylinder would be in this case, it's not that clear, for example, whether you want to consider like something vertical or something with a slant. I think that maybe both of them will have Gromov width equal to the ball, but I think they're probably not symplectomorphic. Yeah, I don't know. But that's a nice question.
Okay, so if there's no further questions, thanks for being here.